For the final topic in this video lecture series, let's take a look at this idea of images. So to do that, let's consider this process where you have some f low, and the f low is equal to your carrier frequency plus the intermediate frequency. So if we had two different stations, one at 1000 kilohertz and one at 1910 kilohertz, when we mix them together, right, when we add the carrier frequency plus the intermediate frequency, we're going to get two different values of f low, 1455 and 2356. So these are two different possible superheterodyne mix frequencies. So when we do this, right, we have this f low or omega low, and when we have these two different channels that we're interested in, let's mix them together and see what happens. So when we mix this omega low together, we see that because alpha minus beta becomes an absolute value of omega c minus omega low. So this part, right, when we do this subtraction of alpha minus beta, right, so when we multiply these two together, and when we look at the mathematics behind this, we see that this term, alpha minus beta, is effectively an absolute value of omega c minus omega low. And that's because cosine, right, has this property. Now this means that this second term, right, this is the term, this is the term where we're going to do, this is our intermediate frequency term that we're going to do our filtering at, right? This is our intermediate frequency, and it's a difference between the carrier frequency and this omega low. So going back to the two channels that we're interested in, 1455 and 2363, we can see that this cosine wave, due to this absolute value and this cosine property, we can see that it turns out that 1000, the absolute value of 1000 minus 1455, is the same as the absolute value of 1910 minus 2365. So it turns out that with this superheterodyne process, these two different channels that we're interested in, if we're trying to do some filtering, we're trying to tune into one of those channels, if either one of those channels is going to end up at the intermediate frequency during our superheterodyne process. So these two channels, we can call them image channels because both 1455 and 2365, when mixed together with the intermediate frequency, are going to appear at the same place. So basically, our antenna is going to receive multiple bands, and these two bands, when we pass them through this, we amplify it, put it through that tunable filter, and at this output, both of these channels would be moved to the intermediate frequency. So both 1000 and 1910 kilohertz would be moved to that same intermediate frequency based on what we saw in this slide. And that's because these two channels, we can call them image channels. So the reality is that those two would end up at the same place, because the reality is it's not actually this at the 455 kilohertz. What we have, is 1000 minus 1455 and 1910 minus 2365, and both of those equal 455 kilohertz. So both of those channels are image stations, and so what your filter should do, this RF filter, as we mentioned, it needs not be a very good filter, but it does need to be good enough that it can completely separate your two image stations. So the RF filter here, in practice, should be good enough to remove the image, but it doesn't need to be any better than that. So as long as you can remove the image, when you make this amplification here, you will only be amplifying one channel and not that second image channel. And that second image channel, again, comes from the fact that we have these two cosine waves are being mixed together like this, and we have this cosine property that effectively results in this term that we're interested in being an absolute value difference between omega c and this omega low. So these two channels, right, these are our two image channels, 1000 and 1910. And for AM radio, the intermediate frequency is usually 455 kilohertz. So these two channels are separated by 2 times the intermediate frequency. They're separated by 910 kilohertz. So your image stations are going to be separated by 2 times your intermediate frequency. And your RF filter only needs to be this good enough to remove that image channel, no better than that. And your IF filter can again be quite good as long as your IF filter is extremely good, right? As long as you build a really nice factory tuned IF filter, it doesn't really matter how close these other 2 bands are, you'll be able to get some really good separation between those. So hopefully you found this series of videos on superheterodyne receiver process interesting. One last thing of note is that this superheterodyne process, it's not just used in traditional radio design, but this process is used in still continuously in many different reception processes, because regardless of what the equipment is and how good your equipment is, it's always easier to make lower frequency filters. And that goes back to the filter design and the idea that we can't make an ideal filter. All filters are going to have some roll off, and these low frequency ones, the total the real amount of frequency in that roll off will be smaller at a low frequency rather than at the high frequency. And so that's why this superheterodyne process continues to be very widely used in almost all communications equipment. Thank you, and I'll see you in the next video series.